got just 22. I made 2 phone calls today. Technically 3. One to one of Don's associates.
Subordinates.
One to Don, and one to the guy at Micro Manipulator.
Yeah.
Just grilled them all.
That's not on me.
Maybe it was 4 cups, but yeah, not very great.
I know. This one here.
Stand? The one on the stand is live. That's live.
Okay. Well, they'll clear out. Yeah. All right. So we're very happy to welcome Professor James Analytis, all the way from Berkeley, the other side, the other ocean at the other side of the country, visiting us today. James got his PhD at Oxford, and then went on to University of Bristol for a postdoc, and then a second postdoc at Stanford, working with great crystal grower Ian Fisher, and then on to his own group at Berkeley. James is, I think, renowned expert in making new kinds of interesting materials from any kinds of elements on the periodic table, making them do cool things, and then measuring those cool things that they do, whatever that may be. So hopefully he's going to tell us about that kind of journey today.
Thanks, James. Yeah. Okay, I really feel really grateful to be invited to give this colloquium at Brown. So thank you to Kemp and to others who invited me here. It's kind of an interesting place to give should I keep this on? Is that okay? All right. To give a colloquium about condensed matter, because condensed matter physicists generally, we really like details and we really like to get into the weeds. And I'm not promising that I won't do that today. But what I do hope to tell you about is really about a way of thinking. So rather than necessarily, I think there'll be some interesting physics on the way, but one thing that I want to communicate is really about the way I think, and maybe that'll be useful to like a broad spectrum of people. Oh, yeah. Thanks. Oh, nice. Okay, so now we are in a more romantic environment. This is a picture of Berkeley. And I'm going to tell you about what really interests me in terms of scientific problems, and that's the problem with interacting electrons. So I study solids, and in those solids, there are electrons. That might not surprise you. And those electrons like to talk to each other. But that's a problem. Before I tell you about that problem, let me tell you about what's not a many-body problem. And that's just a gas. So if you imagine a gas of particles, the reason why we call them a gas of particles is because each one of them can be thought about as an island, all on its own, not talking to the others. And I know a lot about that because I'm from such an isolated island that doesn't like to talk to others. But imagine if you live on one of these islands, and there's lots of them. The whole point about being an island is that you don't need to interact with anyone else. So no matter how they move or what they do, you can basically be treated as a single particle. So even though in principle this is a problem of many bodies, it's not thought about as a many-body problem simply because you can always understand any one particle as a particle by itself. In this case, just one country. So it's not really a many-body problem, it's just many single-body problems. And that's why it's easy to solve. Okay, so what do? I make materials. That's one of the primary functions of our laboratory. And this is what they might come out on a good day. We have nice crystals that come from your synthesis procedure. And then after that, what we do in my lab is that we might post-fabricate them. We'll turn them into devices to measure different properties or machine them to be a nanoscale to look at confinement problems or something like that. Whatever the physics of that crystal might be, we will try and design an experiment around it. And that's kind of the way we approach a problem. Rather than having one large hammer and seeing what materials kind of fit, what we do is that we take materials that we think have interesting fundamental questions and we design the experiment around them. And then finally, we'll just do some interesting measurements, or what I think are interesting measurements. Of course, all of this is done by people. Here's some people making materials in our synthesis lab. There is my former postdoc, Philip Mole, nanofabricating some of its systems, and my former student, now postdoc in Maryland, Sylvia, who was doing some measurements. And so there's three main components to what we look like. One of the things that comes out of interactions is what are known as phase transitions. So the most familiar transition to you is probably boiling water. We just had some to make our tea or our coffee. But when it comes to materials, you have phase transitions from those interacting electrons. And they can have a whole variety of different types of manifestations, not just liquid or gas. One of those phase transitions is, of course, ferromagnetism, where all the spins in an atomic lattice, oops, I don't know how to do that. Here we go. Oop, there we go. Yeah. Where all the spins along the atomic lattice will want to line up. And that's, of course, the basis of your refrigerator magnets. Another one is ferroelectricity. They're the kinds of things that Professor Coretta, for example, is interested, where you might have an electric polarization in the system itself. Another kind of phase transition is known as antiferromagnetism, and that's where all the spins, the electrons on those sites are actually anti-aligned, kind of the opposite of a ferromagnet. And then another example is, of course, superconductivity, where the electrons find pairs with each other, known as Cooper pairs, and they move in harmony, basically, what's known as coherence, and then transport electrical signals without any dissipation. So what I find exciting about interacting electrons in materials is that there's all these unusual instabilities, and those instabilities manifest in lots of different ways, and sometimes they compete with each other, and when an electron doesn't know which one of these phases it wants to fall into. And there are a whole variety that I haven't listed here. Okay. Now, what an interaction is, it's usually an energy scale with which two particles talk to each other. In this case, let's take the example of ferromagnetism. there's some interaction that two spins use to communicate. That's the two islands communicating. I'm probably overusing the island motif now, but you'll survive. At high enough temperatures, if the temperature has an energy scale that's higher than that interaction, those spins can kind of just freely move around according to what we call thermal fluctuations might be. But as soon as the temperature drops below that energy scale with which they talk to each other, then they start to see each other on some time scale and some length scale. And now they start to move in harmony, and eventually all of those spins line up together, and that's what we call a ferromagnet. The specific kind of interaction in this case is known as the exchange scale, and it's in essence you can understand it as the cost and energy of exchanging spins between sides. And so once you have that kind of interaction, you always have some manifestation of it. At low enough temperature, those spins will want to align. The one thing that I want you to take away from this slide is just to remember that I'm using the symbol J for exchange, and that's an interaction scale between two single particles, in this case spins. So just try and remember that for the rest of the talk. Okay, so how do we describe what happens across a phase transition? Well, we often draw an energy landscape. And here's what I have as just a parabola where I have what we call an order parameter. This characterizes what the spins want to do in the case of the ferromagnet. So the order parameter is a measure of what those interactions are kind of driving. In the case of a ferromagnet, it's magnetization. So it's like what the magnetic moment is of these spins aligning together. And that order parameter, we can assign a value to it, 0, for example. And as you go to a finite value, it goes to a higher energy. So obviously, for this particular case, the electrons want to have, the whole system wants to have 0 magnetization. So that's what we call just an ordinary paramagnet. Now, as you cool the system, and those other terms in those interactions start to become more dominant, you can describe the free energy in the system in a slightly different way. So let me just give those things symbols. This is my order parameter, this is my energy. And now I'm cooling the system, and I'm seeing how the free energy of the system actually evolves. And I will see that parabola start to flatten out. And then eventually, it looks like some finite magnetization, or some finite values of that order parameter start to become favorable. This is a kind of a cartoon way of characterizing how a free energy evolves across what's known as a continuous phase transition. And then below that transition temperature, well, now I've got some finite values of the order parameter, which are now at the lowest energy. And in the case of a ferromagnet, for example, there might be 2 of those, plus magnetization and minus magnetization as you've got, and that kind of leads to different domains in the system, so up spin and down spin along different domains of the ferromagnet. So that's basically how we characterize a continuous phase transition. As we tune the system in temperature, we basically say that the free energy can kind of evolve in the smooth way, and eventually a finite value of the total magnetization of the system, namely the alignment of all the spins, is now a favorable state of the system. So that's how we characterize it. Okay. So what's happening in the system? How do we characterize the response of a material that's near a ferromagnetic transition? And again, the magnetization is now our order parameter. That's the parameter characterizing whether we're going through this phase transition or not. And what we're looking at is its response to field. So field B is like you're applying a magnetic field to the system, and you're looking at how the response and the magnetization actually looks. Now, the prefactor to this response is known as the susceptibility. The linear response is known as the magnetic susceptibility. And at high temperatures, all those spins kind of jiggle around, but at low temperatures, they start to align. So how does this value susceptibility, which characterizes the response of our system, evolve as you go to lower and lower in temperature? Well, for a system that doesn't order, the susceptibility just kind of grows and grows and grows. What that means is that it's easier and easier to bend those spins in an applied magnetic field as you go lower and lower temperature. It's basically because those thermal fluctuations become a lot less effective at destroying the alignment of all the spins. But in a ferromagnet, something interesting happens, and this is what I want to tell you a bit about. In a ferromagnet, sometimes what we characterize, because there are now interactions with its the spins in its environment, it's now starting to see all the spins that are around it. The way we sometimes model this, at least in the simplest way, is what's known as a mean field. We say that a little local spin in the middle of a material feels a mean field from all the spins around it. So it's basically an approximation. And what happens when you apply such a mean field is that you get the same kind of divergence of your susceptibility as you decrease in temperature, but then as it goes through the transition, the susceptibility gets cut off. And all of the spins are all aligned, and you just end up having like a constant susceptibility. Okay, or zero susceptibility, depending on the transition. Roughly speaking, and this is not quite accurate before the condensed matter physicist growl at me, roughly speaking, the transition at which your system goes ferromagnetic is proportional to the exchange energy scale. Okay, so the interactions between your spins are roughly proportional to wherever the system orders. So if you've got a room temperature ferromagnet that has strong interactions, if you have a ferromagnet at like 5 Kelvin, it has much weaker interactions usually. Sometimes it means other things, but we'll get to that later. Okay, so how do we characterize what this mean field is? Well, something very interesting happens as you approach a phase transition, and that's what's known as fluctuations. Basically, it's where those spins start to see each other in a local environment, and they start to kind of move in harmony. But they haven't fully formed a ferromagnet in this case. And some of them will be down. So what I'm plotting here in the mean field is what these fluctuations between spin up and black and let's say spin down and white will kind of look like as you approach this phase transition. Now, something really interesting happens in this fluctuating state. And that is a kind of what's sometimes called a statistical symmetry. It's an emergent behavior of the system where you get what's known as scale invariance. What that means is that if I looked at the spatial profile of these fluctuations, so imagine this is like real space in a ferromagnet, then as I go closer to the transition, I will get the same kind of profile of fluctuations, but now over longer length scales. But it'll just be really a multiplicative factor connecting the fluctuations in one part of the system to the fluctuations in the other. So in other words, this is what we mean by, this is a kind of what sometimes people call like fractal behavior or scale invariance. It just means that as the system approaches its phase transition, you have these spatial fluctuations of the spin that don't have an intrinsic length scale to them, except for a cutoff scale. Okay, so what does this lead to? Let me give you one example that's one of my favorites, which is known as critical opalescence. So in this case, I've got a beaker that's half heptane and half ethanol. If you have these in your lab, I strongly encourage you to try this experiment. You can heat the system up these are two colorless liquids, by the way. They're not blue and pink. But if you heat them up, they form a homogeneous mixture. You heat them to about 120 degrees Celsius or so. And that homogeneous mixture is also colorless. So there's either two colorless liquids, this is also colorless. But something interesting happens as you cool the system down to go back to this state. And I set this up a little while ago, and I'm going to show you what it looks like. Okay, so this is my beaker that I had on my hot plate over here, and I'd heated up the mixture, and it became colorless. But now I've put it on an ice block, and you might start to see something happening in the solution. Can anyone tell me roughly what they see? What's that? It looks like fog rising, that's right. The system is becoming cloudier and cloudier and cloudier. Even though when it's cold, the system is two colorless liquids. And when it's really hot, the system is two colorless liquids as well. What happens in between is what's known as critical opalescence. Why? It's those fluctuations, those scale invariant fluctuations that basically have fluctuations over all length scales. What are they fluctuations of? Well, those two liquids, heptane and ethanol, have different densities. So these are fluctuations of density. But they're fluctuations that happen across all length scales. And that spans all length scales of visible light as well, which means that when light enters the solution, it scatters all length scales of light, and therefore the system starts to look white, starts to look cloudy. And that's why it looks white. And that's an example of how those fluctuations evolve across that phase transition. And it's a direct example of their scale invariance, how because they have no scale in them, they can scatter all wavelengths of light. Okay. I understand, Dima, that you do this demonstration in your class, your StatMech class. Yeah, I did, but I ordered the wrong chemical. So I was writing it too quickly to Lucas. It's entirely my fault. I said hexane and ethanol, but it's actually heptane and ethanol. So I know, but then you have to do it under pressure. It's a much more expensive chemical. This is a very cheap way to do it, so I recommend, and safe as well, yeah. Okay. So something else interesting happens in a lot of the measurable quantities that you measure as you go across these phase transitions. And I guess these labels aren't very clear, but this is basically the magnetization of the system, the order parameter, remember, of a ferromagnet, and this is the temperature as you cool across that phase transition. And what you see plotted here just looks like a line, so it's basically how that order parameter evolves as a function of temperature. But what I don't tell you is that there's actually about 10 different kinds of ferromagnets that are plotted along this same scale. In other words, and they're completely different chemistries, completely different elements, it's just showing you that that scale invariance coming from those fluctuations means that no matter, as long as you're the same kind of transition, kind of ferromagnetic transition, you'll always approach and cross that phase transition in exactly the same way. The scale invariance, this emergent symmetry, means that the chemical details of the system that you're looking at become completely irrelevant. And I think it's a really beautiful part of the universality of these statistical symmetries, of these emergent behavior that comes specifically in continuous phase transitions, that you can understand the approach to this transition and almost all of its physical properties just by understanding the statistics and knowing nothing about what elements it's made of, or even what a magnetic moment is, or how the bonding works, or any of the other stuff that condensed matter physicists often worry about. So that universality is kind of an elegant and beautiful consequence of the scale invariance that always happens in continuous phase transitions. Okay. And that's, of course, the connection to, that's basically one of the quantities that manifests in is the susceptibility. And it's one of the things that we spend a lot of time measuring. Okay, let me talk to you about generalized susceptibility. So we spoke about ferromagnets and how you have a magnetic susceptibility. You can apply the same kind of idea to lots of different kinds of transitions and lots of different kinds of order parameters. If it's a ferroelectric, then it's the electric polarization and then a ferroelectric susceptibility. If it's an antiferromagnet, then it's what's sometimes called the staggered magnetization. That's the order parameter, and I don't know what this number is anymore. If it's a nematic transition, which is a kind of an anisotropy in the system itself, then the anisotropy of the system itself will be proportional to what's sometimes called the nematic susceptibility, and the field there could be like a strain, or could be an electric field, or anything that couples to the anisotropy of the system. Okay, so sometimes these different kinds of orders, these ones here, are coupled together. So they come together. So let me give you an example of that. Imagine these are my electrons in my solid, and they want to have some kind of nematic transition, which basically means that they want to become anisotropic. So here's what they would look like if they're anisotropic. But there's another thing that also is anisotropic in the system, and that's, of course, where the crystal atoms are themselves. So imagine if I have a square lattice like this, then the system could also become what we call orthorhombic, so elongated along one direction. And these two things have exactly the same symmetry. And because they have the same symmetry, they couple together. Why is that important? Because you can imagine if I start with my square lattice with my electrons in the middle, and I squeeze it in one direction, then that's basically coupling to basically trying to turn the square into a rectangle, but it's going to have a response in the electrons themselves. And so as a result, by coupling to the lattice with some strain, I can actually couple to the nematicity of the electrons themselves. And that's a technique that we actually used while I was a postdoc at Stanford when we were studying some anisotropic superconductors known as the iron-based superconductors. So we got our crystal, we had a piezo stack. A piezo stack is just something that basically you apply voltage to and it squeezes and expands at will. We could measure the conductivity anisotropy, so basically the resistance of the crystal in two different directions. And you could see how that evolves as a function of temperature. And right on TC, this is where the system becomes, where the nematic order parameter sets in. You can see the susceptibility really start to diverge, just like the susceptibility that I showed you for a ferromagnet. And that's what I mean by generalized susceptibility. Other people picked up on this and started to study lots of different kinds of materials, iron-based superconductors, orthorhombic systems, lots of kinds of things. And we often publish things that look a bit like this. This is known as a phase diagram, where this particular group from Shibachi's group in Japan were changing the sulfur content of a particular iron superconductor, and they could see the nematic transition kind of drop down to zero. But then at that point, what this color plot shows is essentially the magnitude of this nematic susceptibility, so basically how quickly this curve diverges. And so where you see the red color is where it's diverging very fast, where you see the blue color is where it's diverging very slowly. And so they measured this, and they saw something very interesting, that as the transition goes to zero, you actually get even larger susceptibilities. Let me expand on this point. I'll come back to it because I'll lay it out. Because what's happening around here is what's known as a quantum critical point. Okay, what's a quantum critical point? What's a quantum phase transition? So far, we've talked about transitions in electrons that happen at finite temperature. So I'm cooling the system down, and it becomes antiferromagnetic, or becomes ferromagnetic, or whatever, and that's the transition. But let's say I've got another tuning parameter. Let's say I can change the system non-thermally. I don't just have to change temperature, I could change the magnetic field, or the doping, or the sulfur content, or whatever my parameter might be. And let me call that G. And for whatever reason, the transition temperature of this system starts to go down to zero temperature. Now around here, where we have the fluctuations that I talked about, those classical fluctuations in space that we understand relatively well. But at the quantum critical point, you're at zero temperature. You can't think of thermal fluctuations anymore because there is no thermal energy scale. But you do have other kinds of fluctuations, fluctuations that result from the uncertainty principle itself. And so now you actually have fluctuations in both space and time. Okay, and the way to understand that is that you have an energy scale, the exchange, in this case I've written it as whatever the interaction scale is, and there's a function of going down in temperature. Remember how TC was broadly proportional to the interaction scale? Well, that's basically what's happening here. Some interaction scale is vanishing as you go towards the quantum critical point, and that's basically what's happening here, leading to what we now are calling quantum fluctuations, because they're not classical fluctuations the way we normally think of them. Okay, now at this quantum critical point, where you have all of these quantum fluctuations, lots of interesting things happen. That's where some of the more anomalous properties of unconventional superconductors happen, for example. And in fact, in almost all cases that I know of unconventional superconductors, high temperature superconductors, all of those kinds of really exotic materials, almost always they're associated with, apart from the fake results on hydride superconductivity, but the other materials that came before that, almost always there was a quantum phase transition that was associated with a superconducting dome that basically hid that critical point. So people from the very early stages of studying unconventional superconductors started to think that maybe quantum criticality had something to do with the existence of the superconducting dome, of the superconductivity itself. Okay, what are the weird properties that come up? Well, you get lots of interesting scaling behavior that again come up from the scale invariance of the system. In this case, I've got this one unconventional material where the magnetization shows a collapse of all the data. There's this appearance of what's known as T-linear resistivity. Unsurprisingly, it's where the resistivity is linear in temperature. And that's seen over and over again in lots of unconventional superconductors. Our contribution to this is that we connected the T-linear resistivity to B-linear resistivity, and that's what you see, what you see here. So again, some kind of scaling behavior near the critical point. And then lots and lots of these colorful phase diagrams. So people that put together, in this case for this material, strontium ruthenate, this is the power law associated with the resistivity across a critical point, and it looks like it really is an energy scale that's vanishing and leading to this strongly T-linear behavior in the center. This other system, ytterbium, rhodium to silicon 2, where you have a similar kind of critical fan of fluctuations that lead to apparently strongly T-linear behavior again. The moire systems, which have similar kinds of phase diagrams, again indicative that there's a critical point that's of a collapsing energy scale that's connected to the presence of superconductivity. Over and over it comes up, and there's no exception to the example that I showed you, which was the pneumatic susceptibility, the one which was the response of these iron-based superconductors to strain, where you now have this diverging susceptibility right near a critical point. Okay, so why is all this, so fundamentally, this is still an open problem in condensed matter physics. Like, how are these critical points? How do these critical fluctuations relate to the underlying phases in the system? How do they compete with superconductivity, or how do they even assist superconductivity? As far as I know, this is still one of the biggest open problems in condensed matter. Okay. Now I'm going to tell you about something else that happens around phase transitions, which is the existence of domains and domain boundaries. Now, for those of you who remember, we talked about that energy landscape of ferromagnets. Well, in that case, you could have two polarizations of the ferromagnet that could come up. And here I've got a spatial picture of a ferromagnet, where you can actually see how where blue is spin up and red is spin down, and you can see how these domain boundaries kind of form in a real material as you change the field or change the temperature. Other kinds of phase boundaries are the ones that we also were discussing earlier with the pneumatic susceptibility and the antiferromagnets. So here are three materials where these lines here are actually different domain boundaries, where you basically have the pneumatic order is pointing in two different directions. Just as the spin is pointing in two different directions in the red and blue, here these boundaries are the pneumatic orientation is going from left to right to up and down. Okay. So this led to one other thing, which is a result I had in my postdoc in collaboration with the Cam Mollop group that has really kind of haunted me since. So this is about 11 years ago. So here you're looking at domain walls of an iron-based superconductor. So it's one of these materials here. And what you're looking at is it was Bina Kaliski, who was a postdoc with me at the time. And what she measured was, they have a scanning technique called the scanning squid, where they can basically measure the superfluid density or measure where the system is superconducting in different parts of the sample. So you can imagine like having a slab of material, and then you're taking your squid tip and actually measuring where it's superconducting and where it isn't superconducting as you go across. And what she saw was that you got stripes of superconductivity right along the domain boundaries. And I was really curious about this, because what it was showing was that while you're getting superconductivity at the domain walls, like between those different directions of the antiferromagnet or the different directions of the pneumatic order, you actually got more superconductivity than before. And remember that strain plays a really important role to how close the system is to the critical point, right? The whole system, the whole critical transition can be driven by the application of strain. So I was kind of really excited about the idea that you could have like a system that was had one particular order either side of it, but then at a boundary, it was itself near a critical point. And how maybe that could be used to like drive those boundaries really quickly, or look at some anomalous dynamics, or move them in some interesting and useful way. Like when you have these, in other words, that you have some kind of diverging susceptibility, but that only applies to the boundary and doesn't apply to the bulk around it. So I was really curious about this idea, but we kind of left it there. We never did anything with this material because I guess we didn't know how. But it haunted me, and I wanted to see if I could apply it to something else. And that's the next story that I'm going to tell you. Okay, so I was thinking about critical points, and I was thinking about how critical points could change spatially. How you could have a critical point, a system that was near a critical point at domain wall, but nowhere else, and how you could use that to do something useful. All right. And I was reading the literature around, I stopped reading the literature now. But I was reading the literature about, in a completely different field to mine, antiferromagnetic spintronics, which is an area, a specific area of the of like basically applied condensed matter physics, where people are interested in making kind of new, faster magnetic memory. So for example, in the case of antiferromagnetic spintronics, two of the motivations is that they can be ultra fast because you're leveraging that exchange scale. And the second motivation is that, so ferromagnetic components for ferromagnetic memory have all these stray fields, and these create errors when you're trying to pack components together. Antiferromagnets don't have that. And what a series of papers about 10 years ago demonstrated was that you can make a piece of magnetic memory from an antiferromagnet, but in a device that looked like this. And what they did was really the following. You could flood current. So this is an antiferromagnet known as copper manganese arsenide. And you can make this little 8-prong device. And what they do is that they flood current east to west, or they flood current north to south, and they measure a change in the resistance. And their signal looks a bit like this. So when you're flooding the current north to south, you can kind of get a decrease in the resistance. That's what, and this is like a pulse in the north-south direction, like 50 pulses, and you get here. And then you pulse it in the perpendicular direction, east to west, and your resistance goes in the opposite direction. So what they were trying to demonstrate is that this is a kind of memory, like pulsing the current in this direction gives you low resistance, pulsing the current in this direction gives you a high resistance. So it is a kind of a memory, I can see that. Okay, interesting. How does it work? Why does it work? Does it work? So the basic idea is the following. In the system, it turns out, because of symmetry reasons, that when you apply a current, unfortunately also called J here, but it's just a current, it carries a little bit of spin. Okay, and that spin can be imparted onto the magnetic lattice. And what that does is that it moves one of these domain boundaries. So that's the cartoon that I've got there. So you pulse the current, when you flood it with all these electrons, that all of them, or partially spin polarized, they can move one of these domain walls. And when I saw this, I got thinking to that old result that we had at Stanford with Bina. Well, what if these boundaries were themselves near a critical point? Would this be easier because I've got this larger susceptibility, right? I've got a larger response to whatever I'm applying to it. Maybe if we applied the same idea, but now to a system that had boundaries near a phase transition, we would get a much faster, much more robust response. So we tried it. What materials did I work on? Well, I did some research and dug up a series of materials, and I was interested in these layered systems. These are layered transitional metal dietrocogenides. For the experts who are interested, it's a triangular lattice system that's layered with the magnetic ions between the layers, and it's these magnetic ions here that actually have all of the magnetism. Okay, why did I think about these materials? Well, back in the late 70s and 1980s, there was Stuart Parkin and Richard Friend were studying these materials. And they basically they basically measured all of the transition temperatures of these materials as they went magnetic. So here's the material. They went through basically, vanadium, chromium, manganese, iron, like essentially all of the 3D elements in the periodic table. And then they got all of their Curie temperatures, or their can be thought of as their transition temperatures. And what you can see is that some of them are positive and some of them are negative. Okay, what does this mean? Remember, so this temperature is basically Tc. Tc is proportional to the interaction scale, the exchange scale, right? The fact that you can go from one sign to another, what I was thinking was that you must have to cross zero at some point, right? If you're crossing zero, it means that that energy scale vanishes. If that energy scale vanishes, you have a quantum critical point. And that's why I started thinking about these materials as maybe potentially interesting applications of exactly this idea. Why don't we start with these magnetic systems, drive them towards a point where they are now, like by, alloying or playing with the intercalation of these magnetic elements, driving towards their critical point and seeing what happens to their domain wall dynamics. Okay, so this is the exchange scale. Going from chromium to nickel, it seemed to somehow change sign. So I started, this is why, people ask me, why did I work on the iron compounds? It's because of this, because iron was the one that seemed to have a random sign depending on, whether it's niobium or tantalum. It basically changed sign. So I figured iron was maybe somewhere near the critical point. Okay. I got my single crystals. Remember, my crystals look like, my crystals look like this. And then I turned them into little devices that look like this, a little bit like that copper manganese arsenide. So 8 contacts, I flood current through the blue direction or flood current through the red direction, and I look at the resistance change in the middle to see what happens. And what's that? Close to 1/3. That's a good question, but yes, it's around 1/3. This is the disulfide, yeah. Well, the disalinide works as well. It should work as well, but I don't know. Does that structure exist? I don't know. Yeah, okay. All right. And you pulse the current between the blue direction and the red direction, and sure enough, you get low resistance, high resistance, low resistance, high resistance, really reproducibly. Something else was kind of off in comparison to the old data. So remember, they had this sawtooth structure in the other material where every time you pulsed in the up direction, you always got like a higher and higher resistance. We never saw that. Once you pulsed once, it was there. It was always in the same resistance. Over and over again, you would just get the same resistance if you went up, or left, right, left, right, left, right. So in other words, it was a very different characteristic to these other switching devices. It seemed to be more robust somehow. Not only that, but the currents that we needed to use, so this is like 10 to the 6, 10 to the 6 amps per centimeter squared. We were at height of 10 to the 3s, 10 to the 4s amps per centimeter squared. We were like 2 to 3 orders of magnitude lower current and about an order of magnitude faster as well. So we could do it over much shorter time scales as well. Yeah?
James, can I just ask a geometry question?
Yeah.
What does this look like from the side? I'm a little confused by that.
So what we do is, good question. So what we do is that we make, they're planar systems like this, and we either cleave them and have like a thin flake and then machine that crossbar, or we actually machine a lamella. So we cut out a square and make so it's like a 1 micron thick lamella or something like that. And then we machine this pattern on the top. So the crystal facets will be out here, the ones that you saw. So this is false color, obviously, but yes, these are there'll be gold actually here and here. There won't be any gold here. We won't be shorting out the sample. This just shows where the directions are that you're measuring. Yeah. Sorry, it's a bit confusing. Depends on the system, but this particular one was about a micron thick.
So you do it just by scotch tape?
No. For this particular one, we actually they don't exfoliate very well, so we machined lamella for this one. But there are other systems where you can actually exfoliate them and get, even a couple of 100 nanometers or something. Yeah. Okay, so we got the super robust signal, 3 orders of magnitude lower power, 1 order of magnitude faster. You know, everything's coming up Milhouse. Yep, nobody watches The Simpsons anymore, I suppose. But anyway, so okay, but there was something pretty weird about all this. So you could change the intercalation just a little bit from 0.31 to 0.35. So this is so it was about 1/3, but you could actually change the intercalation a bit. And here's something that's interesting that happened. Can anyone see the subtle difference? So these are the pulse trains again, like the north-south direction, the east-west direction, low resistance, high resistance, low resistance, high resistance. Can anyone notice the difference between these two things? What's that? They're out of phase. Yeah, they're like 90 degrees out of phase, basically, right? They're basically what was a low resistance in this one is a high resistance in this one. What's a low resistance in this one? What's a high resistance? What's a low resistance in that one? Even though we're pulsing along the same crystallographic directions. How can that be? Right? We're putting current in the same direction. The spin is being imparted in the same direction. What is changing is a function of just that small change in the percentage, just a few percent in what the intercalation is. And it's like we're rotating the magnetic order in like opposite directions. It doesn't make any sense. Okay.
Can you remind us what's the pure systems electronic property in Albion sulfide?
It's a charge density wave, but I don't think it's... Oh, wait. Is that the one that doesn't...
You sure iron within, let's say, intercalation is not going to be lattice?
Yeah, so we did pretty extensive TEM, that's right, and the iron goes between the layers.
The irons, they don't form clusters inside, they just separate individual.
Not for this compound, they don't form clusters, but it's true when you get to the close to 1/4, you start to get the clusters of 1/3 and clusters of other percentages, yeah.
Are they all ordered?
The 1/3?
Yes, the iron.
The iron is ordered, like magnetically ordered? Or and
No, they
crystal...
form structural order.
Yeah, absolutely. Yeah. They form a triangular lattice, actually. Yeah, for sure. But you can take some out and it'll still form the same triangular lattice, but just this one will have vacancies and this one will have interstitials. But it's okay, yeah. And I think the interstitials, yeah, where do those go? I'm not sure. Yeah. But anyway, why was there a difference? So we did some neutron scattering, which is a way of figuring out what the magnetic structure is in the system. And it turns out you get 2 different magnetic orders with just that small percent change in the ion intercalation. So you get like stripy order in the low intercalation ones, and you get this zigzag kind of order in the other ones. And they have opposite anisotropies. They have opposite resistance responses. And so now it all made sense. This is why we were seeing the opposite response is because these 2 things had different kinds of magnetic order with exactly perpendicular anisotropies. And you might be surprised, well, you might not be surprised to know now that once you had something that was like right on stoichiometry, this signal almost completely vanished. Like the two things completely canceled out. So why does this happen? Well, we worked with some DFT people. We did some calculations. They calculated what all the exchange parameters are. And it turns out that you have to go to your next nearest neighbor interactions. Interactions not just between your immediate neighbors on your triangular lattice, but your next nearest neighbor. And once you do that, you can actually get zigzag on one side and stripy on the other. And this is a little bit like what I wanted to happen, which was the exchange scale changing sign. It doesn't actually change sign. It's the main exchange scale, J1, the dominant one, doesn't do anything. But the next nearest neighbor one seems to evolve from one to the other. And it's because of that we change from one kind of interaction to the other. So it wasn't quite what I wanted. It wasn't quite a system on a critical point with it. Yeah. We haven't done that yet, and I'm not sure if there's a good reason why we haven't done it. I'm trying to think whether the magnetic order is even the same, actually. But yeah, good question. Yeah.
How to change X? Do you do it in single design beam, or you actually prepare different samples with different X?
Prepare different samples with different X. Yeah, so the whole samples are made with chemical vapor transport, and we just have a different stoichiometry. It took us a while to optimize the synthesis. In fact, I think this is a problem with the current work, but the first paper that we wrote about this, we said the intercalation was 1/3 because we didn't think it mattered, but it was actually at 0.31, and then we found all of this rich behavior. We went through months actually optimizing the growth and then finding like the perfect sample where it was right on 1/3, but then all of the signal disappeared. And we're like, what happened? We made these materials like more perfect, but somehow everything didn't work. So but it was because of this, because of these competing order parameters. Okay, how much time do I have left? 5 minutes, okay. So I wasn't quite ready to give up on this idea, and I'll just tell you one relatively quick story, but then I'll finish up, I promise. And that's with a totally, okay, so boundary between two orders, but it's not exactly a boundary of critical points. I'll skip this bit. Well, you can actually extend these arms of these devices, and actually you can switch the signal like 30 microns away from where you're applying current. So there's kind of these non-local effects as well. So whatever is happening to the domain boundaries, it's actually extremely effective, and it's propagating them like tens of microns away from the active area of where you're applying current. So there's something really, I think it's something quite neat, much more effective than other systems. Okay, so I wanted to look at another system where this idea, it's okay to have your biases as a scientist, as long as I have my preferred ideas and I'm going to pursue them, even if they're wrong. But I was going to try at least with this one other system, which is on a metal insulator transition. This is 1T tantalum sulfide, and the system forms a different kind of order. It's not magnetic, it's called a charge density wave. And it turns out that if you slow cool the system, it forms this nice pattern. This is an STM pattern, and it's an insulator. But if you quickly cool the system, it actually forms a metal. So that's kind of neat. Well, here's the data for that. So that's kind of neat, because what it's telling you is that basically by just the cooling rate that you use for the system, you can go from an insulator to a metallic transition. So I really thought this might be another system which might be on the border of a metal insulator transition. Okay. We were seeing some super weird signal. We made all these devices. Finally, once we landed on the right geometry, you can have the same kind of effect of blue pulse, red pulse, high resistance, low resistance. It turns out that it's like because it's a border of a metal insulator transition, it's like orders of magnitude larger signal than what we were seeing in the previous systems. But what's going on? Well, again, I collaborated with my favorite squid collaborator, Bina, who's now at Bar-Ilan University. And she could take one of our devices and actually use the squid technique to image the current. So this is when you apply the small current on the system, you have a Biot-Savart field from the current itself, and that's the blue, these are the polarities of the field on either side of the flowing current. And you can take the derivative of this data and actually look at the current density. So what you can see across this device is basically where the current is flowing. What's happening when you pulse the device? So remember, we're going from these low resistance to high resistance, low resistance to high resistance when we're pulsing up and down. Okay. So what she found is that the current is actually, once you pulse it and once you flood the system with a bunch of current, it actually localizes the current carrying part to the edge, and the rest of it becomes an insulator and doesn't carry any current at all. So somehow, the boundaries now are carrying the current. So the boundaries of the system near a metal insulator transition are the ones that are driving all of the physics. And if you pulse in the opposite direction, the B direction, you start to see this break up, and the current goes back into the bulk, and you can do this repeatedly. We can even change the direction of the current, and we can control where on the system the boundary is carrying the current, and we can actually switch from what boundary state is carrying it. But we still actually have no idea what the boundary is made of, like whether it's the metal insulator boundary or what exactly it is. But again, this happens at very low currents, very low powers, and it just goes to show, in terms of the morals, conclusions and morals, if there are any, is that we start from an idea, which is systems, exotic systems near critical points, connected to this really abstract problem of understanding high-temperature superconductivity. It gave me some motivation to think about how this could be used in a different context, and so we looked into systems from a completely different field, spintronics, to see if you could use the same kind of idea to do something interesting with boundaries. And it turns out that so much of those effects actually happen at the boundary. And I think it's nice to come full circle now and see how even if your original motivation might not be the underlying physics of something you want to investigate in a new system, it's important to come with new ideas to a field that didn't expect them, and you'll still find things that are interesting. So with that, let me just thank you all, and please take any questions.
This niobium sulfide.
Yeah.
So do the niobium disulfide layer do anything to the J exchange factor?
Well, very likely it's an RKKY interaction, meaning that it's the itinerant electrons in the niobium sulfide that are actually mediating the magnetic interaction between the ions. So even though I've got a J1, J2 model, I think the reality is that it's an RKKY interaction. So those J's are connected to the itinerant electrons.
So if you add a strain field along the structure, would you be able to, this J likely will distribute exponentially?
That's a good idea. The carrier density is too high for us to gate it right now, but it's a really interesting idea to try and do that somehow.
It doesn't mechanically just strain it.
Oh. That's a good idea. No, we haven't thought of doing that. That's a really interesting idea. Thanks, Sean.
Thank you, Jim, for this interesting talk. In the niobium sulfide system, did you observe the non-volatile memory effect in the longitudinal resistivity? You measure the Hall effect, right?
No,
you measure all perpendicular, right?
But it's not Hall effect. Hall effect implies there's a magnetic field. So it's in the transverse resistivity. So it's still even in field. It's basically the anisotropy in the conductivity tensor that you're measuring, even though it's a transverse context. There should be a longitudinal signature as well. So let me think about it. It just so let me draw this for a second. Okay, so you're pulsing in this direction, and if you apply a current along here, you'll measure a transverse resistance change. But you actually won't measure anything across here because you imagine that, so basically if you've turned this into one Néel vector, so L is in this direction, then basically the perpendicular pulse will just turn it into this Néel vector across here. So you're always at 45 degrees to it. So the RXX, the longitudinal resistance, won't show a signal along this direction, but it will show a signal along this direction.
So this device is very effective at low temperature. Can you raise the temperature to a room temperature and make it useful?
Excuse me? So I think it depends on your application. But the current problem is that you need an exchange scale that's large enough to get up to those temperatures. And none of the systems, even in theory, are predicted to be that high. The only one that's predicted to be that high is if you replace tantalum with tungsten and had tungsten telluride or tungsten selenide and intercalate those with magnetic ions. The problem is those materials don't exist. So I'm working with a colleague of mine in chemistry, Carbon Abediako, where we're trying to think about how to make those materials artificially and intercalate tungsten telluride or tungsten selenide, and then those transition temperatures will be should be at room temperature and be useful, as you said.
Okay, I have kind of no other questions. Maybe a philosophical kind of question. So I was kind of struck by, with your iron compound, when you tried to make it more perfect and you got the most perfect crystals, it didn't work.
Right.
In the sense you didn't get the signals that you want. So like a long time ago, there was a pejorative for condensed matter physics as the physics of dirt. But are you your results kind of showing maybe that we should really embrace that as the right way to think about condensed matter physics? Like, is there a lot more interesting physics than dirt?
Yeah, I'm just wondering why I'm being publicly bullied like this.
I think it's a good thing. Yeah, it's like a positive.
Yeah, no. I understand what you mean.
I am also a condensed matter physicist.
No, it's okay. So, yeah, I think so. How do I? While it's, I guess it is an interesting point that perhaps we should embrace, that disorder is a tuning parameter that can take us between one kind of phase and another. Condensed matter physicists have known this for quite a while. But here it's pretty explicit that the disorder isn't just a way of kind of making a system kind of less interacting or somehow confused about which direction, which is what the role of disorder usually is. It is actually stabilizing one kind of magnetic order or another. So I like that kind of angle that somehow disorder has made the magnetism cleaner, even if it's made the crystal dirt. Yeah.
Okay, one more question.
Okay, so this is going to be a philosophical attack on you.
Okay, that sounds great.
So
I'm really glad I came.
The phase diagram you draw, this quantum critical point, can you put it up again?
Yeah, for whereabouts? Which one? At the beginning? Or?
At the very beginning.
Oh.
What was this, almost like a genius out of a bottle?
This thing?
Yes. Okay, so this yellow part, it looks like you liberated a quantum fluctuation from this QCP point all the way to room temperature. So usually we teach quantum mechanics, we tell students that, well, at high temperature, the system is dominated by thermal fluctuations, so equal partition principle works. And then at low temperature, you have to worry about quantum fluctuation, the uncertainty principle works. The crossover is where the interesting things happen, and then, well, it depends on what you are interested in. What you are plotting here looks like if you sit at a QCP, you look upward, everywhere is quantum fluctuation. That's misleading, isn't it?
Well, I didn't put a number.
I know you're not responsible for this.
I didn't put a number on here.
I know you're not responsible for this, but
well, is it misleading? Well, I don't think so. So because I think it's a major challenge in the language that perhaps folks in this field often use to describe like systems near a quantum critical point and how far in temperature like those critical fluctuations can kind of be felt. On the other hand,
I never understood that.
yeah, well, I can try and explain it to you, I suppose. But I think on the other hand, things like keep popping up in lots of different contexts, and where you do see, I guess, a continuum of the behavior stretching from the critical point itself, if you believe it exists, through to behavior that seems to be affected at much higher energy scales. Now, what sets that scale and how we can cut it off, I'm not sure, but here's another example with the pneumatic susceptibility, where here in Shibauchi's data, what they saw is the largest pneumatic susceptibilities really, and pneumatic susceptibility, don't forget, is associated with this transition, which is the anisotropic pneumatic transition. So the susceptibility is associated with this order parameter, right? But it's largest where the transition itself seems to vanish. So yeah, I think it's an ongoing challenge about whether how we match those two those pictures that we expect quantum critical fluctuations to be cut off at relatively low energy scales, and yet we have all of this, I guess, what you'd call phenomenological or anecdotal evidence that seems to suggest that there's still some behavior near a critical point that stretches up to pretty high temperatures. The T-linear resistance is probably the biggest example of that, but no one's been able to connect that to critical behavior anyway. But there's lots of, I'm not sure how to respond to you out of that. I do think it's a challenge in the field. I am biased and I like the idea of criticality, but I do think it's a problem that theoretically, if not just in principle, to understand how those effects stretch from the critical point up to those very high temperatures. But, yeah.
All right. Yeah, thanks for a really wonderful talk.
Yeah, thanks.